Hey folks, welcome back and welcome to our online students. Today we're going to take a look at something called the electromagnetic spectrum. And the electromagnetic spectrum is energy that's being emitted from things. And we have recognized this as a bunch of different things. We might recognize visible light, and we might recognize infrared and ultraviolet. And if you're a Marvel fan, you might recognize that gamma radiation is how you make superheroes. So all of these things are examples of electromagnetic radiation. Now, as it turns out, what we're able to see is just this narrow band right here called visible light. That's what we're able to see with our eyes. Now, we're able to feel some things, like if we go over here into infrared, you feel that as heat energy. So if you feel like heat coming off of something, you might feel the infrared. But we just see in that narrow band. And so there's a lot out there in the universe that we're just not able to see, which is really curious. I find this fascinating. There are organisms, there are critters that can see outside of our visible spectrum. Like mosquitoes and snakes can see in infrared. Well, that's kind of cool. Why can they do that and not me? Well, because mosquitoes and snakes feed on warm-blooded critters, and it helps them to see us when we're hiding in the woods. Like I hide behind a bush, you can't see me, but the mosquitoes can, because they can see in infrared. You say, well, why can't I see in infrared, right? What if I'm a vampire, right? That would be a cool adaptation. You can't see in infrared because you are warm-blooded. And because you're warm-blooded, if you could see in infrared, you'd be blind from the heat given off from your body. So that doesn't work. It doesn't work for us. Okay. So we just see in this narrow band, and we use instruments to help us to see stuff outside of that. Now, some interesting electromagnetic radiation, the aurora borealis. How many people here have seen the northern lights? A few people have. It's pretty darn awesome. And sometimes on a clear night here in Duluth, if you look north, you can see these. Sometimes you have to get away from the city. But it's really an amazing sight, absolutely amazing sight to be able to see this. And what's happening? This is electromagnetic radiation from the sun, hits atoms in our upper atmosphere, causes those atoms to wiggle and jiggle, and then they give off electromagnetic radiation of their own, and we have the northern lights, which is kind of cool, kind of cool. Now, the atomic spectrum is the light that's given off from atoms when we add energy to atoms. And each atom is going to have its own spectrum, which is kind of neat. It's like each atom has its own fingerprint, its own spectra of light. Some might be visible, but some might be in other ranges of the electromagnetic spectrum. And visible light, this is just what we see. We call it visible light. It's all the colors and such that we see, but there are critters that see outside of that. There's a shrimp in the ocean that sees outside of infrared and ultraviolet, and I just find that fascinating. It's like, can you imagine seeing colors that nobody else can see, right? And then somebody says, what does it look like? I'd like to describe it to you, but I can't because you can't see it. It's fascinating, just fascinating what nature does. Now, electromagnetic radiation, that's any form of radiant energy, and like there's gamma rays and X-rays and radio waves and microwaves. There's all kinds of waves, all kinds of these waves here, lots of different versions. We just see the visible spectrum. And there's a famous dead person. I think this is the first famous dead person besides maybe Avogadro that we've talked about or going to talk about, and that's Sir James Clerk Maxwell. The name is not important. I will not ask you to memorize names, except when I ask you to memorize names. Like Avogadro's number, you got to know that one. You have to know that one. But Maxwell, no, you don't need to know Maxwell. I'm sure his mother would be upset, but she died a long time ago, so it's good. All right, so he postulated, he said that the electric field and the magnetic field are perpendicular to each other. And what does that mean? Well, here we have a diagram showing an electromagnetic field. We have blue and we have red. And we have an electric field which is blue, which is like vertical, okay? And then perpendicular to that, we have a magnetic field, which is like horizontal, doing its own little zigzaggy thing, okay? And so what's the deal with that? One's electric, one's magnetic. One's electric, one's magnetic. Electromagnetic radiation. See where that word comes from? Okay. Now, why do I have a picture of a toaster oven there? Because this is how toasters work. If you have something in your food that looks like this, looks like this, looks like this, okay, looks like that. You recognize this? What is this? Water. This is water. This is another one of those things that if you can't draw that, we're not letting you pass this class. You got to be water. You got to recognize this one. Now, water, we're going to learn later on, has it's polar. It has one side that's a little more positive, one side's a little more negative. So the oxygen side here is a little more negative. Hydrogen's a little more positive. And so this funny looking S symbol here, this means electropositive, electronegative. Okay, so it's positive and it's negative. And if we expose it to electromagnetic radiation, that's kind of doing this wiggle thing like this, that wiggle thing, that magnetic wiggle thing is going to cause this to wiggle and jiggle. Because if you think of this as being like a magnet, where you have a magnet, remember maybe you had this in earth science class where you had a north side and you had a south side, like one side was maybe positive, one side was negative. It's like that with water. And what you're going to do is you're going to take like a magnet and you're going to twirl it around the water, because you see this here is zigzaggy, so it's going to cause like this magnet here to flip-flop, and it's going to cause the water molecules to wiggle and jiggle. And when they wiggle and jiggle, they heat up, and that's how your microwave makes hot food. Now, if you want to do an experiment, you can stick something in the microwave that doesn't have water, like a styrofoam cup without any water. You stick that in the microwave, turn on the microwave, and then you pull it out. It's like, why did this cup not get hot? Because it doesn't have water in it. And you could take like a ceramic cup, again, without any water in it. Now, you could also play with it like with a microwave with something frozen. If the water is frozen, then these water molecules are all tied up in a lattice network. They're like all locked in, and they can't wiggle and jiggle. So microwaves are not really good at thawing things out. Not really good at thawing things out. All right. More than you probably ever wanted to know about microwaves. Or maybe. Okay, stupid story for you. When I was in the Army back in Desert Storm, we had these meals, MREs. I don't remember what it stands for. We called it Meals Real Evil. But they came in these plastic bags, and yes. Meals Ready to Eat, thank you. Okay, that's what they stand for. And so you wanted to heat these things up. And at that time, they didn't have like a little chemical burner thing to heat them up. So what you would do is you would take your MRE and you'd lean it up against the antenna of your tank, and then you go back into the tank and you key up the microphone, and it would blast out a bazillion watts of microwave energy, and it would heat up your food. And so we would just, like this, and it just took a few seconds, because this was like a microwave oven on steroids. And then people would be like, what are you calling us for? And we're like, no, we're not calling you, we're just heating up our food. And they're like, knock that off. And they're like, yeah, but we got hot food. Yeah, it's the little things. Now, the relationship between things like wavelength and frequency is this equation here. So this is our first equation. Now, on this equation, we have our wavelength times our frequency, which is like a V with kind of a little funny side here like this, is equal to C. And what this means here, this is our wavelength. So wavelength, and this here is our frequency. Frequency. And then here we have the speed of light. The speed of light. And how these things are measured. We have units for this. So wavelength is usually measured in meters. Usually measured in meters. However, sometimes it's measured in nanometers. And nanometers, and the reason that they kind of flip-flop on this one, It's like all the equations you have to use meters. But sometimes we convert to nanometers because that's where the visible spectrum is for us. This is what we're able to see. So oftentimes in an equation or a question will say, oh, calculate the wavelength, but tell us what it is in meters. So that would be another conversion. We'll show you how to do that. Now frequency, this is like how many times a wave passes per second. And so we'll say the units on this is per second. Okay, so like a line and then per second. But sometimes people will get fancy with their mathematics to try to impress their boyfriends and say it's s to the negative first, which mathematically is the same thing. It's just like putting the s below the line. Okay, same thing. Now speed of light, the speed of light is 3 times 10 to the 8th meters per second. Now up here it's 2.9979. Close enough. If you use 3 times 10 to the 8th, we're good. I'm not going to fight you over that one. All right, so that's the relationship. That's the relationship between all these things. And sometimes frequency, we say per second or reciprocal seconds, and sometimes we say hertz. Like if you take your finger and you lick it and you stick it in a light socket, you get a little surprise. That surprise is going to happen at 60 cycles per second. So we say the frequency is 60 cycles per second or 60 hertz. It hurts a lot. I've tried this. It's a long story. You got to watch SNL reruns. Now this is the atomic spectra for hydrogen. Now hydrogen, if we take hydrogen as a gas and we add energy to it, those electrons will move up and down, they'll do some dancing, and we'll end up with this spectrum here. And I'm just going to dim the lights here a little bit here. Dimming the lights, okay. And so you get these lines here. There's 4 of them. 4 of them in the visible spectrum. There's others outside the visible spectrum. But that's unique to hydrogen, and only hydrogen does that. Other elements will make lines, but the lines will be different. So it's like a fingerprint for hydrogen. Only hydrogen does this. Now the absorption spectrum, that's just the opposite. It's like the photonegative. Like if you have an Apple phone, you hit the home button 3 times really fast, that's what that looks like. If you don't have an Apple, I'm sorry. Okay, so it's just the opposite, just the opposite. So here's the lines and here's the lines missing. Is all. Each element is unique. Each element's got its own special spectrum. Now, another famous dead person, Max Planck. He took a look and he wanted to see how's energy related to all of this stuff. Okay, so energy, he's got a couple of equations. He has energy is equal to Planck's constant times the frequency. Okay, so we got to put some terms in here. So here's energy. And energy is measured in joules. And frequency is still measured in hertz or reciprocal seconds. And then we have this thing here called Planck's constant. Planck's constant. Because if you discover something, you get to name it. So he named it. Now the units for this is 6.626 times 10 to the negative 18th joule seconds. I'm doing that from memory. Did I get that right? Negative 34. Ah, dang. All right. Negative 34 joule seconds. That's joules times seconds. Okay. So that's a constant. That doesn't change. Now, just mathematically, looking at this equation, this stays constant. How do you know it stays constant? Because it says so. If this gets bigger, what happens to the energy? Gets bigger, right? Because this is a constant. They're equal to each other. So if this goes up, then this has to go up. This goes down, this has to go down. It's a mathematical relationship. Now the other relationship that we get from this, Planck's equation is that energy is equal to Planck's constant here, Planck's constant times the speed of light divided by the wavelength. And all we did for this is we took this equation, we solved for frequency, which is just the speed of light over the wavelength, speed of light over the wavelength. Okay, so it's just a little substitution. Now this shows us the relationship between wavelength and energy. So if the wavelength gets bigger, if this down here gets bigger, then energy gets smaller. Okay, all right, so just kind of relationships here. Just relationships. All right, now, oh, this is an old one here. Okay. Now, Max Planck came up with this thing called quantum theory, and that is to say that energy is quantized. These electromagnetic radiation here, it's quantized. We have tiny little packets of radiant energy, And Einstein had some things to say about this, and we'll take a look at that stuff too. And you're going to be like, whoa, all these famous dead people like Einstein and Planck and Maxwell and Schrödinger. It's deep stuff, deep, heady stuff here. Okay. But basically, Max Planck said that this electromagnetic radiation comes in these little packets of energy, tiny packets of radiant energy. And it says here, having values restricted to whole number multiples of a specific base value. And that's just a bunch of gobbledygook. All that means is that you're going to have whole numbers, okay? So like packets of energy. It's kind of like steps, like stairs. I'm on one stair, here's the next stair. 1, 0, 1, 2. Not 1.5, not 1 3/4, 1 and 2. Nice even numbers, discrete, even whole numbers. Okay, and we're going to come back to this. We'll come back to that. All right, that's Planck's equation. Now, why do we care? Here's one reason why we care. So wavelength can be emitted from lasers. So you can take a laser and you can tune the laser to different wavelengths. And you can tune that laser so that it'll be absorbed by certain pigments or pass through certain pigments depending on the wavelength. And so you can use a laser then to zap things like birthmarks and tattoos. And this is all based off of Planck's equation here. Now, this guy here is a doctor. He's a dermatologist here in Duluth, which doesn't really matter. What matters is the fact he's got a laser gun. That's like reason number 537 to become a doctor. You get laser guns. So he's got a laser gun, part of his practice. And this machine here, he gets to tune it. He tunes the laser gun depending on the pigment of the patient's skin so that it'll pass through the epidermis, the upper layer of the skin, but then be absorbed underneath. Planck's equation. Okay, Planck's equation. All right, so here's a patient who has some birthmarks and doesn't want these birthmarks. So he tunes the laser so that the laser gets absorbed by those birthmarks but passes through the other stuff, the epidermis, and fries those things off. Birthmark's gone, right? Now, if you got a birthmark in other places, maybe you don't care, but sometimes, people get self-conscious about this, don't want that, all right? Okay, now here, this is a lovely story. Look, here's Paul. Now, apparently, this person was tight with Paul. It might have been another guy, a gal, I don't know. But Paul was no longer the thing anymore. So Paul had to go. So patient goes and talks to the dermatologist and says, make Paul go away. And the dermatologist says, did you get a restraining order? He said, well, yes, but I need this to go away. He pulls up the sleeve. Okay, well, okay, we can take care of that, but it's going to cost you a bunch of money. It's going to hurt like hell, but we'll make Paul go away. And that's what they did. They burned Paul right off of the skin there. It hurts, and it is expensive. They charge you money for this. All right, Planck's equation. So before you run out and decide, I'm going to go get me some new sleeves, remember, it's really expensive to have these things removed. It can be done. You might have some scarring, and it's going to hurt, And your pocketbook's going to be a lot lighter, but it can be done. All right, so that's all Plancks equations. Now, here's a question. Mathy type question. Calculate the wavelength in nanometers. Oh, look at that. We've got to convert meters to nanometers. Of light with an energy of 7.85 joules per photon. All right. So I want to calculate wavelength, and I want to, let's see, it gives me energy. So really, I just need to rearrange this equation here and solve for wavelength. So that's going to be a little bit of algebra here. I'm going to take the wavelength, I'm going to put it over here, put my energy underneath. I've got energy underneath there, and up on top I've got Planck's constant times the speed of light. I did my math correctly. Then, what do I do here? Well, I need to put my numbers in here. So that's going to be Planck's constant, 6.626 times 10 to the negative 34th joule seconds times the speed of light, 3 times 10 to the 8th meters per second, all divided by energy. And it tells me I've got 7.85. So 7.85 times 10 to the negative 19th joules. 10 to the 19th joules. And then it asks here, what region of the electromagnetic does this light fall? Okay, so I got to do some math here. Now, before I finish, before I do this, and if you've got a calculator, it's good to plug these numbers in. And some calculators, depending on your calculator, if you don't put brackets around it, what it'll do is you take negative 34 and then you times 3 times 10 to the 8th. It'll take negative 34 times 3 times 10 to the 8th there, instead of the whole number. So depending on your calculator, you're going to have to put those brackets around there. Now when we're done, we know that wavelength is in meters. So if we cross out units, we have joules up here, joules down there. Those go. And then we have seconds, and then here we have reciprocal seconds. So it's like below the line there. So those go. And then we're left with meters. So that's a good sign that we have it set up correctly. Now when we're done, we do all the math on this, we should get some number. I'm doing my, yeah, okay. Some number. Do we have a number? What do we got? 2.5. 10 to the negative 7. Okay. Let's get one. Oh, I guess it doesn't. Oh, we need one more sig fig in there. 2.53. Okay. Now, I say 3 sig figs because this is what we measured. These two are constants, so those don't affect our sig figs. I shouldn't say constants. Those are, well, I guess they are constant. Those are exact values. Okay, like conversions. Okay, so 3 sig figs, and this is in meters. Thank you. So this is very small number. And it's 10 to the negative 7th, but I need to convert that to nanometers. So I'm going to do a conversion here, and I want to end up with some nanometers. So if I have nanometers is what I want to end up with, I'm going to put nanometers up here, nanometers, okay? And then down here I'll put meters because meters need to cancel out. Okay. See, meters cancels out and we're left with nanometers. So then here's the question. How many nanometers are in a meter? One times 10 to the 9th. There's a billion of them. Okay, so 1 times 10 to the 9th. Now you could just leave that as is and put 10 to the negative 9th down here, because negative 9th meters is a nanometer. Same thing. Okay, So if we do that, if we go 2.53 times 10 to the negative 7th times 10 to the 9th, I ended up with 253. 253 nanometers. 253 nanometers. Okay. Now, any questions on that? Okay. All right. Now, then one last kind of thing here is something called the photoelectric effect. This is something that was explained by Einstein. And he's this smart guy, had bad hair, trust me. And we're going to talk more about him coming up with quantum theory. But the question that people had was, why is it that when you shine light on certain metals, they give off electricity? And what he postulated is that there's the electromagnetic radiation, which is quantized. If it reaches a certain threshold of energy, it will kick off an electron off of that metal. And then the electrons will flow across that metal and you'll get electricity. So we have a certain threshold frequency. So minimum frequency of light, which is a minimum amount of energy, will cause these electrons to get kicked off of metals. And some metals are better at this than are others. Now, this brings up another interesting thing. Have you ever put something metal in the microwave? It gets exciting when you do that. Like if you take tin foil and you throw it in the microwave. I did this once. The kids were like, the kid when he was little liked Nutella. He's like, Daddy, I like Nutella. And I was like, okay, well, I'll get you some Nutella. Open it up, it's got this foil wrapper on the top. So I peel off the foil wrapper, stick it in the microwave. Why do I stick it in the microwave? Because he wants it soft so he can spread it on his whatever, right? Okay. I'm a good dad. So I'm like, okay, let me just put this in the microwave. We'll just zap this for a few seconds and you'll just spread this like Skippy, right? So I put it in the microwave and all these sparks go flying and smoke and everything. And the kid's like, woo, yeah, do it again. Because I missed that there's just a little bit of foil that I didn't take off of there. And I thought, wow, that's interesting. Oh, wow, that made sparks. I wonder what happens if I put a spoon in there, right? So stick a spoon in there, no sparks. I'm like, oh, no sparks with the spoon, but it did with the little, well, what if I put a fork in there? So I put a fork in there. Oh, forks give you sparks. Spoons don't. What's the difference between a fork and a spoon, right? And like, well, that's interesting. This sounds like a job for science. So the reason this works is, according to Einstein, you've got a certain wavelength, which means a certain energy kicks off these electrons. The electrons flow across the surface. Now, if that surface comes to a sharp point, like a corner of a piece of tin foil or the tine, those are those pointy things on forks, they're called tines. If it comes to that, those electrons fly off and you get sparks. But if you have a spoon, spoons don't have sharp pointy things on there, right? Unless you're spooning wrong. Okay. And so, that came out weird. Yeah, that was weird. Lost my chain of thought here. Ah, yes, microwaves. Okay, so don't put metal in the microwave. Now, if you have a hot pocket or something like that, sometimes they have metal foil on there, but the edges are smooth. They don't have sharp, pointy edges, and that will help your microwave to crisp up your hot pocket, okay? But don't put anything sharp or pointy in there, or you get a surprise.